Hello, welcome to Unit 4, Lesson 5b. Today we're going to be talking about half-life, which is the time it takes for a certain quantity that is decaying exponentially to decrease by half. So for Activity 1, Got Caffeine, we're talking about how caffeine has an average half-life of about 6 hours. So if a healthy man consumes a cup of coffee that has 100 milligrams of caffeine at 12 p.m., we're going to check here for understanding what are the two key quantities that can be measured in this problem. So the first one is a half-life here, and that equals 6 hours. The second is that we have 100 milligrams of caffeine. That's the amount that he drinks, the amount of caffeine in his cup of coffee. And then 12 o'clock p.m. and that is the time. So our key quantities are that 6-hour half-life and 100 milligrams of caffeine. Now we're going to use these key quantities to solve the practice problems for this video. So each of the following expressions describes the amount of caffeine in the man's body some number of hours after consumption. And every expression has a different exponent representing the amount of half-lives that have passed. So we're going to use the table to figure out how many hours those half-lives are representing. And if the half-life is 1, we know that 6 hours have passed because a half-life is 6 hours. So we're going to fill that in. And if 3 half-lives have passed, we just multiply that by 3 and we get 18. And if it's 1/6 of a half-life, it's going to be 1/6 of 6 hours, which is 1 hour. Now when we write the expression, only the exponent is going to change because that is our time factor. When we write that in, our exponent is going to be the half-life. So in the top one it's 1, and for the second one it's 3, and for the third one it's going to be 1/6. And notice that when we're talking about half-life, so when our rate of decay is that 1/2, our exponent is the number of half-lives, not the number of hours. Now we're going to check for understanding about what these values represent. So the 100 we know is the initial amount, right? The initial amount being the number of milligrams of caffeine that we start with. And then the 1/2 represents the decay factor, right? So in this case, when we're talking about half-life, that's always going to be 1/2. And then the exponent represents the amount of time that has gone by. And since we're talking about half-life, it is specifically in terms of the number of half-lives that have gone by. Now question number 2 is asking us to write a function g that represents the amount of caffeine left in the body h hours after it enters the bloodstream. So we're going to say g of h, right? So we're always going to have our time variable in the parentheses there. And for this equation, our decay factor needs to be in terms of hours, which we actually worked out in the last equation. We determined that over 1 hour, the decay factor is 1/2 to the power of 1/6, right? Because that's 1/6 of the half-life, all raised to the power of h, which stands for hours. And to simplify that equation, we can just plug in 1/2 to the power of 1/6 into our calculator to get 0.89 raised to the power of h. Part B wants us to explain why g of 6 equals f of 1. So we know that g of 6 is the amount of caffeine that would be left after a period of 6 hours, right? Because we just talked about our expression g of h being in terms of hours. And we know that f of 1 is the amount of caffeine that is left after 1 half-life. And that was the original equation we were working with. So we know that 1 half-life equals 6 hours. So I think we have fairly deduced that g of 6 is equal to f of 1. This next question asks, how are these two graphs the same and how are they different? So I'm circling the y-axis here, and you'll notice this measures the amount of caffeine in milligrams. And the y-axes here are the same, right? Because they both measure the amount of caffeine in milligrams, and they're increasing by the same value on both graphs. However, the x-axes here on the bottom are different. So they're both measuring time, but the one on the left is measuring time in hours, and the one on the right is measuring time in periods of 6 hours. Another way of saying that is it's measuring time in terms of half-lives. Now it's important to notice that even though we're measuring time in different ways here, it's still, both of these graphs are representing the same amount of time overall. So to find the amount of caffeine 3 hours after consumption, which input value should we use for each function? So our first function is g of h. This is our function in terms of hours. So we have our initial amount, which is 100. And then we have our decay factor, which is 0.89 for this function, raised to the power of h. And if we want to find that function for 3 hours, we just plug in 3, right? Because this function is in terms of hours. So just rewriting that function with 3, replacing h as the exponent. And for f of x, this is our half-life function. So I'm going to write this out real quick. It's 100, the initial amount, times half, which is our decay factor, to the power of x. And since we know 1 half-life is 6 hours, we can just put in 1/2 here, because a half of a half-life is 3 hours, because 1/2 of 6 is 3 hours. So just plugging in that 1/2 value into this equation, and both of those represent 3 hours. Now this last question asks, how much caffeine do you think is left in a healthy adult after 24 hours? So we know 24 hours is the same thing as saying 6 periods of, 4 periods of 6 hours. And we know 6 hours is that half-life. So we're going to plug in 4 into our half-life equation, which is 100 times 1/2 raised to the power of 4. You can also plug that into our hours equation by plugging in 24 for 24 hours. And either way, both of those equations will give you the same result, which is 6.25 milligrams of caffeine left after 24 hours. So at this point, you should be able to analyze a decay factor in a half-life problem, which we know is 1/2. The decay factor will always be 1/2 in a half-life problem, because that is how much the initial amount is decreasing by over one period. The other goal was to find the growth factor for both whole number and non-whole number intervals. We've been talking about fractions here, so I think we can safely say we covered that.